All right. So I'll share my screen and we'll get started. What we're talking about here is we will be running simulations with Python for this module so that we can kind of work with probability and statistics by blowing them off and just actually running a bunch of experiments, right? So the first thing that I'm going to do here is I'm going to make a brand new repository to hold all of my code. And as a refresher, to make a brand new GitHub repo, github.com/new. And in my case, I don't want this to be part of my personal account. What I want this to be part of is the Codeup classroom so that all the instructors can contribute. And the repo name should be statistics-exercises, okay? So put in here Hopper as well. Hopper statistics exercises. This will be public. And then I'm going to create a blank repo. Now that I have a blank repo, I'm going to grab the clone address here. That's the most important thing. Copy that clone address. And then if I'm in the appropriate directory, the appropriate parent folder, remember my Hopper directory should be a very similar version to your Codeup data science directory. So I'm going to clone this empty repo. And then I'm going to rename it so that on the internet, y'all will see it labeled as on GitHub, you'll see it labeled Hopper, but on my computer, I'm going to call it just statistics exercises. And then we'll change directories into statistics exercises. Okay. What I'm going to do inside of here, I'm going to save two different files. That visualizations file, I'm going to save the code for that. Again, that's a whole lot of matplotlib where we just want to focus on the outcome, not the code itself, but it's there for you if you need it. Hopper statistics exercises viz.py. There we go. And then I'm going to save a copy of basically a copy of the curriculum as well. So what's static here, I have the live runnable IPYNB. And it seems to be labeled, saving the file as a text file, which is silly. I'll fix that. So I'll remove simulation. And then I'll rename simulation.text to simulation IPYNB. Okay. I don't have, I'm not talking to the database yet, so I don't need an env file. If I don't have an env file, I don't need a gitignore yet necessarily. It's generally a good idea to have a gitignore though. So we'll make one real quick. And a nice little refresher of what does go in gitignore. Always put env.py in your gitignore. Add ds_store. That's like a default file, auto-generated in Max. It's kind of keeping track of your folder preferences and your view preferences. But like if Brian and I are working on the same project, we don't want to share that. We don't want to get each other's preferences. So I want to ignore that. And then there's a folder called IPYNB checkpoints that I want to keep off of version control as well. And then PyCache as well. So I'll save that. And now if I do end up talking with the database and move a copy of the env file in here, it'll already be ignored. All right. So at this stage in the game, I can fire up a nice little notebook here. And we can jump in. Okay, so what I'm going to do is restart the kernel from the top. And this is a verbatim copy of the curriculum. So y'all aren't missing anything. This isn't a separate notebook. It is like literally the curriculum. So what we're doing here is we're going to work through some probability exercises using random number generation through NumPy to try and simulate the real world. And what would a statistics and probability module be without using dice and coins? Well, we'll be doing that, but we'll also be building things as real world as we can here in these simulations, okay? So the first thing I'm gonna do is make sure I've got pandas and NumPy. And then since I'm generating these visuals, I'm importing that Viz library. Then I'm setting my random seed. Now, does this mean that if you set your random seed to 29, you will get the exact same random numbers in the exact same order that I do? No, but the randomness underneath the hood will have something in common, which makes things more repeatable. In case we were doing like a scientific research, we'd need to be able to have repeatable processes. Generally, what folks do is put their favorite number in there. It's just integers, okay? And now that we've imported NumPy, I'll introduce you to some new friends of NumPy that you might not have met these functions. So there is an entire module, an entire part of NumPy that is just for randomness. And here are some of the tools we'll be using in this lesson and that you can use to make simulations around things in real life, right? np.random.choice. What that does is we provide a list of whatever options we want. This could be a list of strings, a list of numbers, a list of dictionaries, a list of lists, it could be anything. Really what we're gonna do with choice is use strings and numbers, right? The string heads, the string tails, right? And np.random will pluck one of those at random, or two of those at random, or however many you specify. Uniform will generate numbers between a lower bound and an upper bound in a uniform distribution. Uniform, to repeat, uniform is the mathematician's way of saying fair, like a fair coin. The number of heads should theoretically be the same as the number of tails. That is a uniform distribution. Same thing with a die, right? Six-sided die, each one of the pips has the equal likelihood of coming up. That's what a uniform means. The random function will generate numbers between 0 and 1, right? And if we want random integers, bless you, if we want random integers, the function is randint, if you needed whole numbers. And then we have another function called randn, and that's the n is for a normal distribution. And then there's another way of generating normal distributions with np.random.normal. And with np.random.normal, we would specify the mean and the standard deviation. And then we get back numbers that fall in that distribution. Okay, let's take a look at our first example. So you're at a carnival and you come across somebody offering you a game of chance, as people tend to do at carnivals. You pay $5 to roll 3 dice. This is the problem setup, right? Is this the most data science-y problem that's ever data science? No, but it's a fun, elementary hello world of probability, right? If the sum of those dice rolls is greater than 12, you get $15. You triple your money. If the sum of those dice rolls is equal to or less than 12, you get nothing. So assuming the dice is fair, should you play this game? And what would change if our winning condition was a sum being greater than or equal to 12? And these little differences in the setup can have a larger impact. So let's take a look at how we could simulate this problem with Python code, okay? What we're gonna do is run a whole bunch of experiments. With probability, we wanna run things a lot of times. Just like flipping a coin, we wanna flip a coin a lot of times, not just 3 or 4 times, right? And what we're going to be creating here, remember 2 things. The first thing is we're going to roll 3 dice at a time. And that is that where we're trying to make the Python code match the real world, the n dice. This is the number of things we're doing per experiment. We're rolling 3 dice per experiment, right? Per trial. The number of trials is 10,000. So the number of trials, what that is, folks, that's the number of experiments we do in a row. Okay. So let's take a look at what the code's doing here. We're going to roll 3 dice at a time, 10,000 times to see what the outcome looks like. np.random.choice takes a list. So we have the list of numbers 1 through 6 here. That's how we get a 6-sided die. And we are running 30,000, we're rolling 30,000 dice. That's what that n trials times n dice is doing. It's rolling 30,000 dice. Then the reshape here is reshaping things so that we have n rows. That means 10,000 experiments, 10,000 trials, right? And within each trial, we have 3 dice at a time. That's what that n calls is doing. So I'll give you an example. When we run this, we see that the first trial was the list of numbers or the array 645. The second trial was 631, 122, etc., all the way up until we have 10,000 trials. So I'm going to leave that on the screen. I see a hand from Jeanette. Go ahead, Jeanette.
Yeah, I'm kind of trying to wrap my head around the first 2 lines here. So you're setting n trials and n rows to 10,000?
Mm-hmm.
Okay.
This may feel like new syntax. We're not trying to throw you a curveball here. But
no, it's very simple, but I didn't know that Python would accept that, because you're technically assigning something kind of,
mm-hmm.
Yeah, it doesn't look like Python would accept that. So that was interesting.
Yeah.
Okay.
It's the first time seeing this. You don't need to do a bunch of flashcards about this syntax. It's not going to be the answer to a project or a piece of exercise. But in this example, the reason why we're writing 2 different variables pointing to the same number is to try and share a sense of the shape of the data. That each row is a trial, right? Each row in this matrix, which in reality, I don't have any dice on me, but a row in a matrix like this is how many dice you're rolling at the same time, one time. So if this game is roll 3 dice at a time, that's why the length of each row is 3. So that's what the n dice is. And that's the number of columns in each row. And that's what the syntax is doing, is giving 2 different variables the same value. So don't get too hung up on that. What we're really trying to show is that we're rolling 30,000 dice, but we're arranging them 3 dice at a time for 10,000 different experiments.
Hey, Ryan, I have one question. Look, from this one, the way you are assuming or assigning the value to the variables, right? It means while we are doing this, we need to be smart, which one to assume a row and which ones to assume a column, right?
Mm-hmm.
Looks like.
Yeah.
Now, if you do the opposite way, then it's gonna mess everything up.
Yeah, we gotta keep our thinking straight. The rows is the number of trials we have in our experiment.
Mm-hmm.
And the columns is the number of things we're dealing with per experiment, per trial. So if we were only rolling, I'll do something a little simpler. np.random.choice, 1, 2, 3, 4, 5, 6. There's similar syntax that takes a size argument, and it's rows times columns. But let's see if we just roll this on its own. This is only one die, right?
Mm.
And if I say here size, what if I want to roll 2 dice at a time? Right? 2 dice at a time. Y'all are with me on this example? What if we want to roll 2 dice at a time 10,000 times? Maybe not 10,000. Let's just do 10 times. Keep it simple and small. We can pass a little tuple here, 2, comma, 10. Oh, I did it backwards. This should be 10, 2. There we go. So we're trying to represent reality here. So if we're rolling 2 dice at a time, 10 times in a row, our size is 10 by 2. And you'll notice this could be written similarly. (10 by 2 on the size with a dot reshape. So 10 by 2 on the size just rolls 20 dice, right? But our reshape here, roll 2 dice at a time, 10 times. Oh, I keep doing it backwards. So you'll see, sometimes you'll see, or you can use the size argument, or you can use reshape to take an entire list of 20 dice rolls and form them into the right matrix. Did that speak to your question, Rajram?
Yeah, yes, Ryan. Thank you for explaining.
And if I mix up my numbers and I do a 2 by 10, well, what I'm doing now is rolling 10 dice at a time twice, which is different.
Hey, Ryan, so I'm confused when the first one that you did where it has the n trials times n dice, is that basically the same kind of format as the size where it rolls that? Like, okay, so it's not rolling it 30,000 times.
It's rolling 1 die 30,000 times and then reshaping those 30,000 into 10,000 rows of 3.
Okay, that makes sense. Thanks.
So I'll put this into the chat here. These are the same thing. Roll. Here we go. And there we go. Cool. So really it's about getting this matrix to have the right shape you want it, where the number of items per list is the number of dice or coin or whatever, the number of things that are occurring in each trial, and then the number of rows is the number of trials. And we want that number to be high so that we can have more trust in it, right? If we just rolled a random number once, we can't have a lot of trust in what's going to come up. So far, so good? Awesome, awesome. This right here, just getting the setup, getting this matrix set up correctly is pretty important. So we need to make sure, and I'll do this 2 different ways. This is rolling 2 dice at a time with 10 trials. And this is, notice I switched the 10 and the 2. The size is the same. The size is rows times columns, right? It's 10 by 2. But there's a difference between rolling 2 dice at a time and rolling 10 dice at a time, right? Okay. So now that we have this array of arrays, right? How can we sum things up? Well, remember our good friend .sum on NumPy and Pandas. We can sum by row or column, right? And what we're doing with the sum here is we're summing by row. So see this first row here is 6, 4, 5. Well, that sums to 15. The second row is 6, 3, 1. That sums to 10. Are y'all with me on the cell number 25 that I just ran? This is going back to the original problem of you're rolling 3 dice at a time, and the carnival hustler is telling you that if you sum greater than 12, you'll triple your money. Okay, so I'm going to hit that visualization library to hide a whole bunch of matplotlib that generates the following. What we're looking at here, folks, is a histogram, a distribution of all of the different possible sums of 3 dice. The lowest possible sum is 3, highest possible sum is 18 for 3 dice. And what we're looking at here in the shaded region are the sum of the rolls that sum to greater than 12, not including 12. So just visually, geometrically, if you think about what the payoff could be, there's payoff at 13 and above. So the proportion of shaded to unshaded is your chance of winning, right? Because we see all possible outcomes here. What we can do computationally to this list of sums, this array of sums, is compare that sum to the number 12. And remember, NumPy, you don't have to write loops for NumPy, you just use a comparison operator. Is the sum of 15, that first row, is that greater than 12? Yes. Is the sum of 10 greater than 12? No. And what we can do with with a list of Booleans, you can actually take, we don't even need the as type, we can actually take the mean of a list of Booleans and we get the proportion that are true. So the percentage chance of the time that we win is about 26% of the time, and visually that works out. Just a little bit more than a quarter of the time you triple your money. That's not terrible. But now we can build out the problem a little bit more. So we can generate our expected winnings as a function of the win rate times the amount of money you're winning. So that $15 isn't coming out of nowhere. That $15 is coming from the problem setup, from the carnival game setup. You'll get 15 bucks, 26% chance of winning 15 bucks. So that's 15 times 0.26. That means about each game is worth, you could, on average, your expected value is about almost $4, $3.90. But what do they have you paying to play the game is $5. Well, that means the house is going to win, doesn't it? Most of the time. So if the cost of the game is $5, we can calculate our expected profit per each game as expected winnings minus the cost. So we're paying about $1 each time to play the game. You might hit a run of good luck, you might hit a run of bad luck, but if you ran an infinite number of games, we could prove that on average, you're paying about $1.05 to play for the pleasure of thinking you can win more, right? Are y'all with me on this setup with the rate of wins being the number of times the sums were above that threshold? The expected value is the payout times the likelihood. And then payout times likelihood minus the cost means that the house is winning here. Are y'all tracking? Well, I see some nods. All right. Well, what if we change the game a little bit? That's what this next setup is. If we change the game to greater than or equal to 12, that's different. That means that our chance of winning is the blue shaded region plus this bar for 12. which increases our chances a little bit. It might be enough. So we calculate the number of wins as the sums of trial greater than or equal to 12. So we moved the threshold. We calculated our win rate. That's going to change because we've increased the amount of outcomes that produce a win. Then we calculate expected winnings given the cost. And it looks like if you can change the game just that much, you'll make about 59 cents a time per game when you include the threshold rather than exclude that threshold. So if you can talk the carny into changing the rules of the game a little bit, you can hustle them. That's not too shabby. Let's keep going with another example. This one is less about about dice and more about reality. This one was, I think Zach wrote this one. The no rest or relaxation. There's a 30% chance that my son takes a nap on any given weekend day, right? 30% chance on any given weekend day. This would also seem to indicate that if the child napped on Saturday, they still have a 30% chance on Sunday, that these are not dependent on each other, right? These are independent. What is the chance that that Zach's son takes a nap at least one day this weekend? And what is the probability that he doesn't nap at all? So let's do our setup here. The probability of taking a nap is 30%. That's what that P nap is. The number of days is the same thing as the number of columns. We're assigning two variables to point to the same thing. And the reason we're doing this is to remind you that n calls is the number of things we're doing per experiment. We're assuming 2-day weekends here. Just like above, we were assuming because of the game was 3 dice, the number of calls was 3, right? Now the number of simulated weekends is going to be a whole bunch. That'll be 10 to the 5th power. So that's 10,000. So 10 with 5 zeros, or 1 with 5 zeros after it, right? So we'll set that up. Now, the np.random, the .random here will generate some numbers between 0 and 1. Okay, so we'll say that there is a nap if it's less than our probability of taking the nap. Remember, probability of taking the nap is 0.3. Some of these values are less than 0.3, most of them aren't. But with the comparison operator on this entire matrix, we can compare all of the pieces of data where the probability or that number was less than a probability of a nap, and that can produce back an array of Booleans. So pulling our head out of the numbers a little bit, this first column is Saturday. Second column is Sunday. This, what I have highlighted is the first weekend, then the second weekend, third weekend. So recalling our setup said, what is the chance that he takes a nap at least one day? That's the same thing as calculating the number of rows here that have at least one true. Okay. So we can sum up. I know these are Booleans, but if you sum Booleans, they act as ones and zeros. This goes back forever in computers, ones and zeros, trues and falses, offs and ons. We'll sum each row. And our options are 0, 1, and 2. 2 means 2 naps, 0 means no naps, 1 means 1 nap. Okay. And each element of this array is its own weekend or its own simulated weekend. We have 10,000 simulated weekends here. So we can visualize this. And we see with a 30% chance each day of taking a nap, the likelihood of taking 0 naps is actually pretty high, right? This should actually be, if we have a 30% chance of taking a nap, that means we have a 70% chance of staying of no nap, right? And we're just shy of 0.5. Well, that's 0.7 times 0.7, right? And then we have a little less chance of taking 1 nap, and 2 naps in a row, one Saturday, one Sunday nap. Oh man, I love this Monday afternoon. We're talking about naps. But the chances of having 2 naps in a row is much lower, right? Theoretically, we're setting up our experiments here, but theoretically, if we have a 30% chance of taking a nap on one day and an independent chance of taking a nap on the other day, we multiply those together. That's 0.09, which tracks visually right here. Just like the chance of taking 2 naps was 1 minus that 30% chance of taking a nap times 1 minus that 30% chance of taking a nap, which is 49%. So this is like theoretically, but we're not in the theory part. We're in the just hack it out with some Python part, right? So we'll sum everything up and say, hey, where the sum was equal to or greater than 1 was about 50% of the time, just a little bit over 50% of the time. Geometrically, that's the area of 1 nap plus the area of 2 naps, which is just over, it's like 51%. The probability of no naps is 49%. And there's no other option. There's no 3 or 4 naps. So both of these numbers sum to 1. It's all possible outcomes. So far, so good. Go ahead. Yeah.
I'm confused. I might have missed something. So why isn't the probability just the 30?
It's 30% chance per day, but the original setup of the problem, 30% chance that the child takes a nap on any given weekend day. What's the chance that the child takes at least 1 nap across 2 days? So you're totally correct, Stephanie. If we were only focused on just Saturday, there'd be a 30% chance. But if we're looking at Saturday and Sunday in a row, we have Saturdays on this first column on the left, and then Sundays on the column on the right. And we're not assuming 3-day weekends or holidays or anything, right? Did that speak to your question about how the 0.3 turned into 0.49 and 0.51?
Yes, thank you.
Awesome. Glad you asked about that. Very glad you asked. So I'll reiterate that. On any given day, the chance of taking a nap is 0.3, but on 2 days in a row, taking a nap would be 0.09. We're multiplying independent probabilities together. That matches the visual right here. The probability of no nap is 1 minus the probability of a nap, right? So if we're just looking at only Saturday, 70% chance we get a Saturday. We have a Saturday no nap, right? And if we wanted to calculate those in a row, we could calculate those in a row. 0.7 times 0.7, that's 0.49, which is the same as what this chart is showing us. There's just no rounding, there's just less rounding errors there. Cool, cool, cool. I've got one more example, unless y'all have some questions about this nap setup here. The array setup, the outcomes. We're okay? All right, I've got one more example for y'all. And remember, these examples will help you work through the exercises. The exercises will get harder than the examples, but all of the building blocks we're covering here so far. So let's build a data frame here. Instead of just dealing with a NumPy array, let's build a happy little data frame to answer the following problem. What's the probability of getting at least 3 pips on 3 different dice rolls? Well, we know the chance is 1 out of 3 on each dice roll. but we're rolling 3 dice at a time, so 3 dice per trial. And we're going to run a whole bunch of trials. So let's gin this up. Let's code this up. The number of simulations we're going to run, we're rolling 3 dice at a time, but we're going to do 10,000 simulations. The number of dice per experiment is 3. How do we know? Because it says 3 dice rolls at a time. We're doing np.random.choice on the numbers 1 through 6. We multiply rows times columns, so we generate 30,000 dice rolls. And then we reshape our array or our matrix or array into a matrix to be 10,000 rows of 3 dice each. And then we'll make a happy little data frame here. Let me break this down a little bit because this one line of code is doing a little bit of lifting here. Let's make a data frame out of our roles. We'll start here. Let's prove it's a data frame. And what we're seeing here is the columns. The 0 is the first die, the 1 is the second die, the 2 is the third die. Index 0 is 3 dice at a time. Index 1 is another experiment or another trial of 3 dice at a time. Okay. And our question is, we're asking if the number 3 exists in anywhere in each row. So let's say df has a 3. And this will be a Boolean containing if any one of these rows has a 3. So the first row, no 3s. Second row, there's a 3. All right, so let's gin this up. We'll do I realize there's a lambda here and I don't want y'all to be thrown for a loop by the lambda. So I'm going to make a nice little function, has a 3. And my argument will be the row here, and we'll return if row.values, if the number 3 exists in the row's values. So if you ever see a lambda that's freaking you out, just slow down and write out the function that has the guts of that lambda, and then run it on one thing. So has a 3 this could be has a 3. And for our row, let's send in our data frame, just the first row of df.head1. Oh, that's because it's called roles. So roles, the first row doesn't have one. Let's check the second row. Roles, this is going to be iloc, give me 1 to 2. Yeah, this is our second row that has a 3 in it. So let's end that up and then say has a 3. That's the second row. 3, and it does. It's right there. So I want to run this function. I want to apply this function on every single row. So I'm going to show you how to do that. Has a 3, and what we're going to do here, this isn't df, this is on the same data frame. We're going to do roles.apply, and if you don't do anything special, apply will apply that function to the whole column, but I want it to apply per row because each row is a single trial, right? So I'll apply our function has a 3 to axis is 1. And then we'll do a rolls.head. So does this row have a 3? No. Does the second row have a 3? Yes. Does the third row have a 3? Yes. All down the line. And I'm so focused on the number 3 because that's in the setup of the problem. What's the chance of getting at least 1 3 and 3 dice rolls at a time? So what we have here, 10,000 trials, a new column that holds the outcome. And then what we can do with this Boolean column has a 3, we can say rolls dot has a 3 dot mean, and we get the proportion of times we roll at least 1 3. And we have a number of win conditions. Rolling a single 3 is a win condition, rolling 2 3 is a win condition, rolling all 3 3s is a win condition. So like here's our experimental outcome showing percentage chance of rolling at least 1 3 on 3 dice. Right, so 42%. We could also set this up theoretically. If you've ever done like, if we wanted to approach this rather than rolling 10,000 dice, we could set this up theoretically. We have a 1 in 6 chance of rolling a 3 on a single die, right? And then we have a, so this could be a 1/6 chance for each one of these columns. So we're really just summing up the probability of rolling at least 1 3 plus the probability of rolling exactly 2 plus the probability of rolling 3. Okay. Cool. I'm gonna check the chat real quick. Awesome. All right. So let's see. We're gonna get into these exercises and let's see. You can, it's your choice if you make a Python script or a Jupyter notebook, right? It's dealer's choice there. This first question, how likely is it that you roll doubles when rolling 2 dice? I would set this up with 2 different arrays and see how many times they're the same thing. So I'll do this. Would y'all like me to work this first one for y'all just to give y'all a little bit of a transition from lesson to exercise?
Yes, please.
Cool, happy to do that. So let's set this first one up. How likely is it that we roll doubles when rolling 2 dice? So here, let's say I made 1 die, np.random.choice, 1 2 3 4 5 6. It's a nice fair die. And let's say that I want to roll 10,000 of these. I'm showing y'all a different way of setting things up. Instead of making a matrix, I'm going to make 2 different arrays. So far, so good. Die 1 is a whole bunch of rolls. Die 2 is a whole bunch of rolls on die 2. And what I can do here is set up matches. Samesies. I love this variable name. It's going to be samesies. So this will be a Boolean that holds true if die 1 and die 2 are the same at the same index. Holds true if die 1 and die 2 in the same trial, the same role. They don't have to be 2s, they don't have to be 4s, but they're the same role. And how could we set this up? Die 1, double equals die 2. And then a variable called samesies holds true if the values are doubles or not. And this how likely, that's looking for a probability or a proportion, right? So we can say of these samesies, if I get the mean, which is the sum of the trues over the total, we said it's about 16% of the time. Okay. So that one's, like, I didn't necessarily have to set this up as a data frame or as a matrix. I set it up as 2 different arrays here, just a little bit different of an approach for that first exercise. Yeah, go ahead, Brian.
When you were setting up here, I was trying to follow along and I had a problem setting up that viz, whole viz thing. We need to have that for these exercises?
In no way. In no way. It is there to support the visualizations that are in the curriculum, like this blue one. You don't need to run, if you were interested in the code, it's there as reference, but you don't need it for the exercises. Yeah. Cool. So some of these are pretty classic probability problems. Let's see. This one about the number of people in the room. What are the odds that 2 people share a birthday? That one's a pretty classic probability. Lots of algebra on the board if we were taking that kind of an approach, but we're making Python do all the work here. So that'll be fun. We'll have a little bit of time today, just about 20 minutes, and then we'll have plenty of time tomorrow morning to work on these exercises, okay? I'm gonna stop sharing my screen. And I'm open for questions about these setups or anything I can do to help y'all get your bearing